All right. We've done the hardest part. Now let's just coast a little bit. Let's relax and do some solids of revolutions. You might start by saying, Jason, what's a solid of revolution? Well, I'd love to tell you. A region that's revolved. A region that's revolved around a line is a solid of revolution. And I'll probably be abbreviating that. SOR. So what I mean by that is, and again, this is going to look very calculus-y. What if we have a function and we're looking at the region under a function? And what if we rotate that about the x-axis? What does a solid of revolution look like? Well, if we rotate this about the x-axis, then what we get is something that looks like this, kind of like our sideways vase from before. Now this picture is kind of terrible, so here's what's happening. Say we have a region. If we revolve it around some line, the resulting solid is a solid of revolution. So look that we can start like dragging that line into 3 dimensions. And when we drag it all 360 degrees around, all 2 pi radians around, with each radius is essentially the same shape, right? Just in different dimensions. That's a solid of revolution. So we've already been doing this in this video. This is exactly what we did in example 3 with this little guy. Okay. That we modeled it, one of its sides by this. And in that example, we revolved it around the y-axis. In this example, we're revolving it about the x-axis. All right, and that's what we're doing here. It's going to be the same for volumes, right? You'll just get a cross section. But now, if we're doing it around this axis, we'll want a vertical cross section. If you did a horizontal cross section here, that is possible and very difficult. But yes, you could still do a horizontal cross section. You could still do a horizontal cross section and get the right answer here. Let's not do that. Sometimes horizontal cross sections will be easier. Sometimes vertical cross sections will be easier. The more and more practice we do, the better you're going to get at finding that. Example 4. Find the volume of the solid of revolution bounded by the graphs of f of x equals x squared minus 4x plus 5, x equals 1, x equals 4, rotated about the x-axis. We need a picture. You could do this by hand. It would take a little bit. But you could do this by hand. Let's just use Desmos. X squared minus 4x plus 5. X equals 1. And x equals 4. We're looking at this region, the region trapped by this. Did I specify? Hold on. And y equals 0. So the x-axis is going to be our last bounding thing as well. So it's going to be this region right here. Step 1. Draw a picture. Remember we said that all the way back in that first video for today. So that's step 1, we're going to draw a picture. Whoa, not like that. And we have our parabola from 1. So it starts before that. 4. Like that. And we have, this area is getting rotated. And how is that area getting rotated? Well, you can think of like a mirror image right here. And then we have, again, this sort of deal right here. And now this blue solid of revolution is we want the volume of. And the idea here, now we're doing it with horizontal cross sections. But the idea is that any cross section of this volume, sorry, vertical cross section, this is step 2. No, it's still step 1. At any x coordinate now, it's a circle. Cross section's a circle. And what's the radius of this circle? Well, it's kind of hard to see from the picture. But the radius is just going to be the height of the function. What's the height of the function? That. So the volume is just pi times y squared, which is just pi times x squared. Oh, I'm going all the way into step 2 now. I just did a lot. I just went so fast. Rewind. Well, I mean, you can literally rewind, but let me rewind and do things slower, okay? This blue shape is our volume, using what we said about the definition of a solid of revolution. And again, we could either do a horizontal cross-section or a vertical cross-section. Horizontal cross-section for some of it would just be a rectangle. But for others of it, like here, like you get really weird stuff, and it would be like part of a rectangle and it'd be a little bit more complicated. And then there would be some parts where like you'd have to do it disjoint rectangles. You don't want to do that. The vertical cross sections are going to be much easier here. And then pretend that I drew my picture where the x-axis goes through the middle. The height is just going to be the function value. And we're rotating that. We got a circle as our cross section. So what's the area of a circle? Sorry, this should say area. What's the area of a circle? Pi times the radius squared. And then we just substituted. We've done all the hard part. Now it's just chapter 1. The volume is the integral of the area. And here our variable of integration is x. So what is x going from? It's not starting at 0. Again, this is the furthest left that we go. The picture is not great. We're starting when x is 1. And again, we're using x coordinates now because everything's in terms of x. We're going up to x equals 4. Now we just evaluate this integral. We're good to go. That's all there is to this video. Pause the video, try to evaluate the integral, and let's see if we get the same thing. Again, it's really tempting here to use a u substitution. Let this be our u. But the problem is that we don't have a du to do this with. So we're going to probably want to FOIL this out. I don't think there's a way around that. There might be, but I don't think so. I'm going to take the pi out in front. If we FOIL this out, we're going to get, oh, I'm not foiling this in my head actually. X squared minus 4x plus 5 times x squared minus 4x plus 5. Let's do all the x squared terms first. X to the 4th minus 4x cubed plus 5x squared. And then all the next ones. That's going to be minus 4x cubed minus 16x squared. And then minus 20x. And then the last ones, that's plus 5x squared. Oh, color coordination. Minus 20x. And then plus 25 is the last one. I ran out of room. See, I almost had it so all the fourths were here. All the cubes were here. I almost made it nice. So it's x to the fourth minus 8x cubed plus 10 minus 16 minus 6x squared minus 40x plus 25. So that's what this expands out to. Gross. Polynomials are so nice, but sometimes they can have a lot of pieces. Hope you're ready for the power rule, because we got to use the power rule many, many times. That's going to be 1/5 x to the fifth minus 2x to the fourth. 8 divided by 4 is 2. Minus 2x cubed. 6 divided by 3 is 2. Minus 20x squared plus 25x. Evaluated from 1 to 4. I'm going to plug in 4 with a calculator, and I'm going to plug in 1 with a calculator, and I'm going to get the answer. So let's call that integrand f. That's going to be 1/5 x to the fifth minus 2x to the fourth minus 2x cubed minus 20x squared plus 25x. We're curious what happens when you plug in 1. What happens when you plug in 4? Plugging in 4 is giving me a negative number, which makes me nervous. I may have foiled this wrong. I want to check my work. I'm not going to stop the video. I want to actually show you a couple ways that you yourself can double check these things. For example, we can go to Wolfram Alpha and just check that was our foiling correct. These are good things for you to do on homework assignments and stuff. X squared minus 4x plus 5 squared, and it'll FOIL it out for you. X to the fourth minus 8x cubed. We had that. Plus 26x squared, that's the problem. When we plug that all in, what we're going to get now with the fixed thing, when we plug in 4, we're going to get 412 over 15. And when we plug in 1, we're going to get 178 over 15. When we subtract and fully simplify our answer, 412 minus 178 should be 234 pi over 15. 15 is 3 times 5. This is not divisible by 5. It is divisible by 3, though, because you add the digits. You get 9. 9 is divisible by 3, so this is divisible by 3. That's going to be 78, I believe. 78 pi over 5. Let's check our answer. Is the integral from 1 to 4 of pi times x squared minus 4x plus 5 squared dx, is that equal to our answer? Our answer is 78 pi over 5. Whew. Wasn't even worried. There we go. So that's how we can check our answer. And that's how you can find the volume of a surface of revolution. Again, it's much easier, I think, than the earlier ones, because here we actually have a formula and we don't have to hunt for this using what we know about lines or squares or circles or stuff like that. Let me know if you have any questions on this video, and have a great rest of your day.